This was the 1 minus the 2.
I'm going to go through this briefly because I expected very, very, very high average on this. And unfortunately, it wasn't the case. And I want to tell you, like this type of problem, you have to know well. You'll see this thing continually. So I'm going to go through it. I thought I made it clear about this problem, but I could see, it was bimodal, very high grades. A bunch of people, basically any mistake they made was silly. And then I saw some people didn't seem to really have a good understanding even where to begin. If you didn't get your quiz, come on. Who are you?
Lance.
Oh, wait. Is that yours? Yeah. But I want to go through this one. I didn't try to make it in any way, shape, or form complicated in terms of having to be very focused on calculations because the probability of all these was the same. That's the reason I gave this problem because I thought it would just be straightforward. But let me go through this and then before we move on. We'll be going past Bernoulli trials today and getting into more or less something called Bayes' theorem, and this is something you got to be attentive to. Now, this is not in any way a criticism. I'm trying to encourage you. You have to understand something. In the summer, it's 10 weeks, not 15 weeks. When you have gaps in your understanding of concepts, it kills you because everything builds. And I've already talked to the class about the unfortunate fact that a lot of people fail in the summer that I think shouldn't because they just don't try hard. So be careful about this stuff because it'll catch up with you and before you know it, you're failing. So I'm trying to help. So this is a problem and it was meant to be as simple as possible. I'm just going to do it like this. And then I had this. And I called this switch, I think 5. And it doesn't matter what these are. I'm showing you this diagram. Normally what I do is put a lever here like this, but I didn't even bother. You don't need that information. These are all switches. They all have a probability of P of being on. And same here. And what was asked, and I did this sequentially for a reason so you could see logically how you'd put it together. And the first part that I asked, I think it was the middle switch was not closed. Is that correct, first of all? All right. So for this one, what this actually looks like is this. And here's A, and here's B. Now for this one, these are all P, and this is just the standard reduction, and I'm doing it just the way I believe I explained it to in class. The first thing you're going to do is notice the top one, they're all in series, correct, class? So what I can do, because they all are in series, the probability of this switch working and this switch working is really the probability of the first switch working times the second switch working because they are basically mutually exclusive or independent of, or I should say, not mutually exclusive, they're independent of each other. So because of that, I'm going to just do this. I'll simply go ahead and replace that with a switch P squared. Does everybody agree with that, first of all? By the way, if you didn't get your quiz, you can come up here and pull it out of that stack that's on the yellow pad. And I'm going to do the same with this one. Now, the one thing I will warn you about, for this quiz, the probability is all the same. A lot of times they won't be. And that means you're going to have to do the calculations carefully. If you get sloppy, you'll mess it up. Follow me on this class. All right, does everybody agree with that? That's probability of the top one working, bottom one working for part A, or for the first part, correct? Now, the probability of this working is really 1 minus the probability of it not working. Does everybody follow me on that? So now up here, I'm going to say the probability of it not working is 1 minus p squared. Down here, it's 1 minus p squared. I hope everybody remembers going through this. Now, I know the probability of this not working would be the probability of this not working times the probability of this not working. They are independent events. Do you all agree with that? Correct, class? All right, so now what I'm going to say is that means if I take 1 minus p squared and multiply it by itself, I get that. That's the probability of this circuit not working. I'm going through this a little quick, but the solution is online if you look on OneNote. Does anybody confirm that and saw it? Okay, it's there. But I want the probability of it working, so it's 1 minus that would be the probability of part 1, or A, working. So, and I'll call it P of working. I don't remember what this is, but I think I made the probability 0.2, is that right?
0.1.
Or was it 0.1?
Mm-hmm.
All right, if it's 0.1, so that's going to be 10 to the minus 1 squared, 10 to the minus 2, 1 minus 10 to the minus 2, right? That's, well, what, 99, all right? And then you're going to square that, 1 minus that. I don't remember the exact value. You have it. Any of you have your quizzes?
0.0199 is what I put.
That's right. All right, so that's part A. Part B, or the second part, I should say, it's this, where now I say assume that the center switch right here is closed, and I'm just going to make this point one time. If this is closed, then really I have these two in parallel and these two in parallel. This is a conducting circuit where it's either on or it's off. Follow me, class? And if that's the case for part 2, it looks like this. This would be A, and this B, right here. And I just want the probability of a conducting path occurring between A and B. This is the second part. Do you all agree with this, class? All right, for this one, again, probability of this working is P, this working is P. Probability of not working is 1 minus P, this one not working 1 minus P. Therefore, the probability of this section working right here is going to be 1 minus P quantity squared of it not working. Everybody with me on this? There's no tricks here. Now the probability of it working would be 1 minus that. And that's the probability of this section working. Y'all follow me? Now what that means is, I can give this, I'll just call this like P1. That means I can represent this entire circuit by something fairly easy to see if you didn't see it the last time. I can replace all this stuff with just P1 once I calculate it. It's the same here. They're identical in every way. Do you agree with that? So what it looks like is just this. I can have something with P1, something with P1, and I want the probability from A to B. By the way, this is of the circuit working. So the probability the circuit works, or AB has a conducting path, is just going to be equal to P1 squared. I've got to make sure everybody agrees with that. There's no problem in understanding it. Now, if that's the case, and it is, then I can say, well, I'm not sure what P1 is, but I see I got 1 minus 0.1, and that's going to be 0.9. I got to square it, get 0.81. I take 1 minus 0.81, right? And then I multiply 1 minus, and what does that come down to?
0.0361.
All right, so this part is 0.0361. Now, for the final part, by the way, that's the largest answer of these. I think you noticed that. The final one is, well, Now if we say we want the probability of the circuit working, given this is the situation, what I told you, I tried to tell you how to do this, you always break it down in parts. It's the probability of this switch not working, right, times the first part. Now follow me on this and I'll explain. So the total probability of this circuit working, this is part 3 of that quiz. By the way, you came in late, or I don't think you were here for this, but there you go. So the probability of this working and P A to B working, and I'm just going to call it PW right here, is going to be the probability from 1, and that's 0.0199, but it's the probability of this switch being, now you got to multiply it by the probability of the switch not working, right? Because this is the not working value, so it's going to be 1 minus in P, and I'm going to leave this P here, and it's going to be plus the probability of working, which is P, times the probability of the switch being closed, which would be the second part right there, and what was that, 0.0361, right?
Mhm.
Now, one person forgot a calculator, and maybe I didn't state this as clearly as I could. Anytime there's a quiz or test, you're expected to bring a calculator. All right. It is closed book, closed notes. No wearable electronics, and your phone has to be taken out and stuff and put away. But you are allowed a calculator, and that's one thing I want to make certain I said. And this, when you do this, what does this come down to?
0.02152.
Okay. Everybody with me on this? Any questions? Try to make it. This actually, I think we talked about this during the class period before you got the quiz. I think I outlined that kind of problem. All right. Yes, sir.
So, on number 1, whenever the middle switch is open,
Yeah.
you don't factor in the 1 minus P value until the very end.
If it's open, I just asked for the value. I wanted the probability of this circuit working. Make it absolutely clear to yourself. There's no middle switch if it's not working, right? So we find out the value of this. Then we find out the value or the probability of this switch working. Now, I think you see it logically. We could do the P of A over B given, B type of thing, but you can see that what we're really talking about here is if I have those two values and there's a middle switch here, I take the probability of that switch being open times the first, plus the probability of that switch being closed times the second, and that is the overall probability of this working. I might add, you can extend this problem logically. You can obviously see, I could have something where instead of having these two, boy, I'd like to do it this way, but you could easily see where you would have something like this. And I'm just taking one more leg there, right? And then I could put switches in there. I don't ever make them too complicated because you just don't have enough time to go through all the permutations. But you can see, if you understand the basic principles we're showing, parallel, series, and if they're neither, if they're like a delta Y network, then you have to go ahead and figure out what's the probability of the thing working given the switch is open, and then you have to find the probability of it working when the switch is closed, and then you have to go ahead and take the probability of the switch being open times it working plus it being closed, the probability of it being closed, or the switch being closed, which is P, times the value of, or really the probability of that particular circuit working. But that's the way it goes. One thing you should have caught from this one, this is a very important point. This value right here is less than that. And it should make perfect sense if you've got a short here. I mean, even in basic, electrical engineering terms, anytime you have things in parallel, the resistance goes down, and anytime you have things in parallel, if we're just trying to talk about a conducting path, the likelihood of having the conducting path goes up, because if either one works, it works. Okay. Enough on that. Now, any other questions about this? I don't know what the average was, to tell you the truth. I didn't calculate it, but I think Canvas gives you the average. I could be wrong, but I think it does. And now, last class I was talking about Bernoulli trials, and this is, first, it's very, very important, but this is for what I call binary events, where something can or can't happen. It's not something where there is, a continuous value, where it may be, can have a value from 0 to 1 in all possible values. This is something where it either happens or it doesn't happen, and this is real important. So for Bernoulli trials, I guess, anybody not get a quiz? Okay. So for Bernoulli trials, I'll put the formulas up in a second, and I want to go through this fairly carefully. I mentioned that your calculators are able to do Bernoulli trials. Did you all take a look at this in your stat package? All of them, I've taught this class since 2002 in the summer, and everybody always had a calculator that did that. You're going to need that. I'll go through. Well, I'll tell you what, I'm going to put it. Well, before I do Bernoulli trials, let me take a step back. I want to do exercise 1-9.2. As a matter of fact, I'm trying to do this in a way where if you don't recall something, hopefully I can ping your mind and you'll see this. You want to do me a favor?
Read out.
Here. Or you can read it from either place. This is example, or exercise. Exercise 1-9.2. Go ahead.
A combined experiment is performed in which 2 coins are flipped and a single die is rolled. The outcomes from flipping the coins are taken to be head-head, tails-tails, and head-tails, which is taken to be a single outcome regardless of which coin is heads and which coin is tails. The outcomes from rolling the die are the integers 1 to 6.
Okay, he makes one other statement, I think, with the die. He says if the possible outcomes, if you think about, not die, sorry, for the actual coin being tossed. And he says 2 coins, right? Mm-hmm. Or a coin tossed twice is probably an easy way to think about it. All right, you can have 2 heads, you can have a head and a tail and a head, and 2 tails. So there are 4 possibilities. But he says it doesn't matter if it's head-tail or tail-head, I think, doesn't he?
Yeah.
All right, so as far as the possibilities for the coins, you can have head-head, head-tail, doesn't matter which one comes first, so it really, or you could have tail-tail. That means there's 3 possibilities and only 3. Everybody agree with that, first of all? Now, as far as the die being rolled, if I have a die, that means I can have values from 1 all the way down to 6. Basically, that's inclusive of everything, right? Now for the combinations, and remember this always, anytime you have discrete events like this, and you want the total number of possibilities, just take a look at, these are 2, obviously, they're independent events. That one does not depend on the other. You take the number of possible outcomes in the first times the number of possible outcomes in the second, and you get the total number of possible outcomes. Does everybody see this, class? And it's true always. If you had if you had another event, say, spinning a roulette wheel, and by the way, I looked this up, roulette actually has 38 possible slots. And there is a double zero and a zero on a real roulette table, so you were right about that, but that was not how the problem.
Yeah, I didn't read the problems. I was like, oh, okay, I saw later, like, yeah.
Anyway, because I just had to look that up. If you had that, then the roulette would have 38 possibilities, and the total number of possibilities would be 3 times 6 times 38. And you can see it's getting larger and larger. Now, if we're talking about all the possible values, I'm trying to figure out how he says this, but there's a total of, when I take a look at this, 3 times 6, 18 possible values. Do we all agree on that, class? Right. That's it. So now what we have to, he asks the question, I'm trying to.
Write all the elements of the Cartesian product space.
Okay, I'm not gonna do this, but does everybody see what I do is start with heads in the front. And then I'd have 1, 2, 3, 4, 5, 6. Then I'd have heads, tails, 6 more. And then tails, 6 more. How many see this? I'm not gonna write them all out. He asks you to. I really, he asks you to do it one time so it's sort of seared in your memory. And maybe you should. Okay, now what does he ask?
Let A be the event of obtaining 2 heads and a number of 3 or less. Find the probability of A.
2 heads. So those are the this is the coins being tossed, and he wants 2 of them. And then over here, 3 or less, right? So the die itself could be a 1, a 2, or a 3. Do you all agree with that? I mean, just think about this. It's really easy to get casual. Kind of let your mind wander, but make sure you're clear about this. With me? Now, if you look at that, you can tell if he wants the probability of that event, and each event is equally likely. That means there's 18 possible. This is 3. The probability of this is that relative frequency thing, all right? The probability of this occurring right here, I'll call it A. Probability of A would be equal to 3 over 18. In other words, it's the number of events associated with the probability we want divided by the total possible outcomes, or number of events. And that should be 1/6. I don't know if that's the right answer. I caught a lot of wrong answers in the book.
Yeah, you have it correct. It was wrong in the book.
Is it wrong in a book?
It's wrong.
How many looked at that? Just curious. You don't have to, don't worry, I'm not going to chastise if you didn't, but did you notice that was wrong too? It's irritating to me when a book, it's been around for a while, has wrong answers in the example. Okay, that's for me. Is there another part?
No, that's it.
Okay. I'm just doing this, I thought about this last night, and actually yesterday afternoon, I was going through this, trying to figure out the best way to do this, and I thought, I'll start with this. Everybody should see that as in terms of relative frequency approach, that's it. All right. Now we're going to get into Bernoulli trials, and I'm going to do problem 10-1. Do you want me to give you the book to read here?
You said problem 1-10.1. I have it.
I don't think there are problems 10, are there, in here? I mean exercises, I don't believe.
No, they're not exercises, but there are problems.
Yeah. All right, let me erase this and do it. Something else I'll tell you about this. As far as a supplemental thing that you could use. Have you ever heard of Schaum's outline?
Sean's outline?
Schaum's, S-C-H-A-U-M-S. Schaum's outline has something on probability and statistics. I have it. It has an enormous number of problems and solutions. And if you have a problem understanding some concept, and a lot of people will in this class have problems with some things, especially where we're going with this course, it does a magnificent job of allowing you, here's the concept, you go through and you start working, and the way I always recommend you do this, anytime you're doing a problem, don't look at the solutions, don't look at the answers. Work it yourself, force yourself to learn how to think. Then compare the answer you get with what they suggest and see if it's right or wrong. Now, if you have nowhere to, you don't even know where to begin, then look at the solutions, but that will help. It'll help you immensely. It's, you know, when you just dabble, especially cramming on Thursday night, that's where I see people really getting in trouble. This course can really hamstring. I'm warning you about this because I've seen this too often. Okay, now for that problem 10. This is problem 10. It's 10-1.1, right?
1-10.1.
Or, sorry. 1-10.1.
Yep.
By the way, that was a sign, I think, right? All right, let's go.
2 men each flip a coin 3 times.
Okay, so you got 2 men, and they're gonna flip a coin 3 times. So coin toss equals 3 times. Go ahead.
What is the probability that both men will get exactly 2 heads each?
So probability of heads, 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 heads for both of them. Now, this is a problem, just forces you to think. And I want to make sure I get everybody's attention here. So before we do even discuss that, if we have anything with an outcome, either a head or a tail, a 1 or a 0, a diamond or a heart kind of thing, anything that's binary, it either is or isn't, not like 5 outcomes or anything like that. Only the possibility of one outcome or one or the other outcome. Then you use these Bernoulli probability. And the way the book writes them is P of n, and then he'll put, I think, K in here. And I'll explain this in a second. This is equal to n factorial over k factorial, n minus k factorial, and then p to the k, and then actually it's called q, but I just put 1 minus p to the n minus k, and I'm going to explain this. This is the Bernoulli trial probability. So here's what it really means, and I'm going to apply it specifically to the coin toss problem. If you have an event, and you all agree tossing a coin, the outcome can be a heads or a tails. If you assign like a head is a 1 and a tail is a 0 kind of thing. Then, and the nice thing about coin tosses, by the way, if it's a fair coin, heads is as likely as the tails, and that means this part right back here will always be the same. It doesn't matter if you want 1, 2, or 3, heads or tails, or none. So if I'm flipping the coin 3 times, and that means n equals 3, that's the total number of tries or events. Follow me? And of that total number of tries, I'm looking at the probability, now he says exactly, right? Exactly 2 heads occurs. So that means k is equal to 2. So the probability of, and this would be 3, 2, the way I'm writing it, is going to be equal to 3 factorial over 2 factorial, and it would be times 1 factorial here. N is 3, k is 2, so k, n minus k is going to be 1 factorial. Then it's p, and it's exactly 1/2 the probability of the event occurring, and it's to the 2 power times 1/2, and it would be 3 minus 2, or to the 1 power. That would be the probability of having 2 heads giving you flip a coin 3 times. Everybody agree with this? If you just write it out, you'll see it checks the box. That's one of the reasons I think he does these in a way that's so simple. So if you look at this, that value is going to be, well, 3 factorial, 1 times 2 times 3, over 2 factorial, 1 times 2 is 3. And then if you look at the next part, the 1 factorial is just 1, 0 factorial, and I said this before, is 1. You all with me on this, class? By the way, have you found out where you have these Bernoulli trials in your stats package on your calculators? You need to learn this because Friday you're going to get a problem like this, I believe. So you have to make sure you know how to do this. But anyway, down here, take a look. Doesn't matter how many heads, how many tails, this last part will always be 1/2 to the third. You all follow me? Because they're equally likely. So if I have 2 to the third, that's 8. And 3/8 would be the answer for the probability of one person tossing a coin 3 times and getting 2 heads. You'll notice it's the same as one person tossing a coin 3 times and getting 2 tails. They're identical. Just something to take note of. Now, 2 people are tossing the coin and each have to, what's the probability of both of them getting it? They are independent events. Are we clear? Do you all agree with this? That means the probability they get it, both of them, the probability of head, head, and head, head out of three rolls for both of them is really going to be just 3/8 squared or 9/64. And did I post the solution to that one or the answer to that one in OneNote? And I believe that should be clear how I did that. Everybody with me? I'm going to ask you logical questions if I got your attention. Oftentimes doing this helps drive home a point, I think. We're going to go with the same basic premise. 2 men are tossing a coin. Three times. I want the probability of one guy getting all tails and the probability of the other guy getting 2 tails. Now think about that. Follow me on this? Both guys toss a coin 3 times. I want the probability of one of the guys, and I didn't say which one, tossing a coin and getting 3 tails, and at the same time, the other guy tossing a coin and getting exactly 2 tails. How do you do the problem? Just use your logical senses from what I showed you. What do you need to calculate?
The probability of the first person getting all 3 tails.
And separately, the
and
probability,
then the probability of one of them getting
the second guy
the second
getting
guy.
2 tails.
Yeah, 2.
Exactly 2 tails. With me? All right, let's do it. Well, it's really going to be, what I need is a probability for 3, right? With me on this? Maybe I should leave out this Bernoulli trial stuff. So probability nk is equal to n factorial over k factorial n minus k factorial p to the k and then 1 minus p. Oftentimes you'll see this as q. It's just 1 minus p, and it'll be to the n minus k. If you take a look at this, the probability of getting exactly 3, well, that's going to be 3 factorial over 3 factorial times 1/2, and it would be cubed. First, make sure you see that. Just use this, make sure you see it. Everybody with me on this class? And that's really going to be just 1/8, correct? Now the probability of the second guy throwing exactly 2 tails, we just did that one, but that's 3 factorial over 2 factorial, 1 factorial times 1/2 cubed, and that is going to be simply 3/8, right? You all agree with that? I'm not trying to irritate you with this. I'm just trying to drive home the point, because when I give you a problem like this, I really want to make sure you see the logic and how to go about it, not wonder about, I don't know where to begin. Well, do you agree they're independent? So the total probability of the first event happening and the second would just be 1/8 times 3/8, agreed? And that would be what? That's just 3/64, right? Very small. Do you agree with that? Let me see this. What is the lowest, if we talk about all possibilities that the first guy and second guy could have, which one would have the lowest probability? Just use your reasoning now. There's actually 2 possible events.
The guy getting all 3 of them.
For both people, right? Either getting all, actually it's for all tails or all heads, follow me? That's the lowest possible probability. It's 1/8 times 1/8, right? Now you gotta think about this. If it's all tails, tails and tails, it's gonna be 1/8, 1/64. All heads, 1/64. But if the first guy gets all heads and the other guy gets all tails, if we go that route, there's gonna be 1/64 there and 1/64. But these are the extremes. The most likely case is either one or two. Either one head or two. And if you look at this, we're gonna get into things called distribution functions shortly. You'll see that when we talk about the actual probability of things happening versus like outcomes, k equals 0, 1, 2, 3, you'll see the relative peak is called a median, and we'll talk about that. But this is a little further down the road. I want to make that point. In order to use, I'll talk about one other thing in a second, but where you're going to be doing a lot of stuff with these kind of Bernoulli trials is digital signal stuff. When you transmit information, the probability of an error, sending a bit, and this, it's basically, it fits this stuff perfectly, because with digital transmissions, they're either ones or zeros. They just are. And it makes life easy, but it complicates things statistically sometimes because the length of the message can be enormous. Okay. Want to do one more in this section, just to hopefully seal the deal there. Problem 10, or problem 1-10.4.
Football receiver Harvey Gladiator
Oh,
is able to catch 2/3 of the passes thrown to him. He must catch 3 passes for his hit.
So let me do it this way. I know you're moving fast. The probability this guy catches a ball is 2/3. So he catches 66.666% of the passes. A great name, Harvey Gladiator. And now what's the next part?
He must catch 3 passes for his team to win the game.
All right, let me just stop there. To win, he has to catch at least, right? Not exactly, at least, and this is important, 3 passes. Not exactly, but at least 3 passes. Go ahead.
The quarterback throws the ball to Harvey 4 times.
Okay, so now that would be n equals 4. There are 4 passes. Go ahead.
Find the probability that Harvey will drop the ball all 4 times.
Everybody got that? Think about that for a second. Everything he's talking about is Harvey catching it. But now they want something different, don't they? Remember, he can either catch or drop. So that's the binary event. Well, we're talking about the probability he catches it is 2/3, right? But they're asking the probability that he drops it, right? Here's the way I suggest you go with that problem. Consider the drop positive outcome. Can you follow me on this, class? So that means for this first part, I guess it's part A, we're going to say we don't care about the catch. We're going to use, and I'll call it P bar here, is going to be 1/3. That's the probability of a drop. And we want the probability he drops it 4 times, right?
All 4 times.
Now just please focus, because this is the kind of logic that if you don't really understand it, you get torn up on a quiz or a test. So for this one, now I think about, I erased it, but the Bernoulli trials, P of nk equals n factorial, k factorial, n minus k factorial, p to the k, and it's 1 minus p to the n minus k. But now p is 1/3, because that's a positive outcome. This is the number we want to count times he drops it. If we did it the other route, we figure out the probability he catches it 4 times, 3 times, 2 times, right? 1 time, and then subtract that from 1, add all those up. It's a lot longer to do that. This is much easier. Do y'all follow the thoughts on this one? I want to make sure everybody's paying attention. Okay, let's do it. So this is going to be P of 4. That's the number of events. And he drops it all 4 times, right? The drop is a positive outcome. Do y'all follow me on this test? That's 4 right here. Now think about that. That's going to be 4 factorial over 4 factorial times 0 factorial. And then the probability of the drop is 1/3, and it's to the k power or 4. And then it would be 2/3 to the 0. I just make sure you understand how I got those numbers from that Bernoulli trial. How many have your calculators here? I'm going to encourage you to bring them to class always, because has anybody found the statistic package or where you have?
I found like the factorials, and I have a probability package.
That would be probably the one. And if you look at the manual, which calculator?
I've got the TI Inspire.
That'll do it. I know it'll do it. Yeah. Anybody else have anybody tried doing this? You tried it on your calculator?
I've been trying it all class. It's working out so far.
It's working. And what is the calculator?
This is a TI-36X Pro.
I don't know the difference between that and an Inspire. They should all have the same basic stat package on there. And what is the function called?
It's called, I've been using binomial PDF in the stat
Yeah.
package.
That's it. It's if you learn how to do it, you don't mess around the way I'm doing. But it's important to see what you're doing, because there are some things that come up that we'll get to, like what's the probability of having 3, 4, or 5 outcomes out of 10, something like that. So just be aware of this. What's this going to be? Well, the factorial, this goes away, right? And I really have 1/3 to the 4th, right? That's 1/9 squared, and that's 1/81. Is that right? Is that the right answer too? By the way, I posted the answers. It is, okay. Everybody with me? Now what's the second part?
Find the probability that Harvey will win the game.
Okay. Now we have to rethink the problem in a sense. For Harvey to win the game, he has to catch at least 3. So it's the probability of catching 3 plus the probability of catching 4. Do you all follow me? Don't eliminate the 4. So if that's the case, then over here, this is the probability of Harvey winning the game. So now we're going to go back to the original one, and here the probability of he catching a pass is 2/3. Agree with that? So now what I need for the probability of winning the game, that's going to be the probability, there are 4 passes, of him catching 3 of them, plus the probability of 4 passes and he catching all 4 of them. Everybody with me on that? And then the game is won, according to the way the problem stated. So let's just do this. This one, probability of, we've already, well, for the probability of 3 or 4, that's going to be 4 factorial, if you look at the binomial, right? 4 factorial over 3 factorial, and then 1 factorial. Then the probability he catches is 2/3 to the 3, 1/3 to the 1, k is 3, and then n is 4 minus 3 would be 1, plus, and I'll stop in a second, plus the probability of 4 factorial over 4 factorial times 0 factorial, and then it's going to be times 2/3 to the 4th power. Please take a moment, make sure you're convinced of what I just wrote. Do you agree with that? Now, these are calculations that your calculator can do quickly, efficiently, and not make mistakes. Is that yours or mine? Keep hearing it ding. There's something I have to click. All right, what is this going to come down to? So this is really going to be what, 4? Right? And then I'm going to have 2/3 cubed times 1/3 plus, and this is going to be 2/3 to the 4th power. I don't know what that comes down to directly, but did I put it up? I think I put the answers to all these up there. And you have the solutions manual. Anybody?
16/27.
Oh, is it 20, is that right? 16/27, okay. I'll trust you. That kind of a problem will get to you if you don't do these. And this is a fairly simple problem, so I'm trying to make sure everybody's aware of that. You good with this? I'm going to give you some more on the binomial. Please learn how to use your calculators for Friday. That's the only thing I can do is say, I'm encouraging you to do this. The quizzes are not hard, but they require an understanding of the past work, and you're going to see a lot of this builds. Just don't forget your calculator for this one. Now, on to, this is in chapter 2, and I did one thing. I put up some PowerPoint slides from a fellow named Tom Denning. He's a professor here, and he's over at the MRI Center, but he put together a slideshow for this, and it's pretty good. He used to teach this class all the time. And it really highlights the important points. And did you all see the slides, by the way? No. They are on OneNote, I think.
They're in there.
All right, I'd encourage you to take a look. I'm going to go through some of the basic stuff. As a matter of fact, yeah, I can. I want to go through a few of these. The first thing I want to tell you about, and this is a theorem that you have to know very well, it's called Bayes' theorem, B-A-Y-E-S. Has anybody ever heard of this? Bayesian logic. You probably did. Where'd you hear about it? Do you remember?
This year.
Okay. All right. This is real important, but I'm going to show you how it comes about. I'm going to make it as simple as I can. Go back to the Venn diagram business, where we have an event A, an event B, and we look at this, and this is the intersecting area of A intersect B right here. Now, I think everybody remembers this. And this is in a giant, what we call S is all possible outcomes, and that's the space. We try to give people a visual idea of how to imagine this stuff when they're constructing a problem. So if I look at the probability of A given that B occurred, now how many remember this at least from before? I'm not going to ask, I'm not putting anybody in the spot. But what we're really doing is says, well, B occurred. So if B occurred, it means this. It means that this event happened. We're saying it happened. Whatever the event is, it doesn't matter. It happens, right? Now, what is the probability that A will occur given B occurs? So B happened 100%. And if you look at that, think of it as a ratio of areas. So it's really the probability of A intersect B divided by the probability of B. Can you all follow me on that? Just to show hands, I got to make sure you see this. And I'm doing it with area, really in the book we started out with Venn diagrams, no probabilities. What is the area of A intersect B? It's this checkered thing, right? What is the area of B? Well, it's everything there. Now, if you think about what we talked about, the relative frequency approach, if these things are proportional, the relative size to the frequency of the events, then you can say the area here divided by this area would be the probability of this section actually happening, and that would be the probability of A given B. So I'm gonna write it down this way. It's the probability of A intersect B over the probability that B occurred. Do y'all agree with this? You'll notice that the probability, we're assuming B occurred, so in a sense, this is like 100% guaranteed. And now we're taking a look at the sliver of intersection. I mean, the frequency, relative frequency have to be proportional to the intersection area divided by the total area of B. Then we come over here and we talk about the probability of B given A. Now, I'm doing it this way for a reason. You should be able to see it. First, does everybody see what I was talking about in the beginning? Now let's take a look at that. Well, the probability of B given A. If A occurs, all right, so if A occurred, what I'm really saying is this happened right here. And now I want the probability that this occurs, right? You'll notice the A intersect B is the same. Y'all follow me, class? So I can say for this, it's really going to be the probability of A intersect B over the probability of A. It seems almost silly for me to do that, but there's a very important reason. Now if I take a look at this, I can say P of A, or what I can do is say P of A intersect B is going to be P of A, trying to do it this way, save a little time. It's really going to be P of A times P of B given A occurred, is that. Do y'all follow me? You know why I did that? Because I'm going to replace that up here, and this is where Bayes' theorem comes from. So then I come over here and I say, well, P of A given B is equal to, for the intersecting area, I take that as equal to P of A times P of B given A, and then I have to divide that by P of B. I'll change it in a second to make it the way that it always appears in the book. And this is only for 2 event spaces. We can extend this, but not right now. Can you all see? That means if I multiply both sides by P of B, I get P of A given B times P of B is equal to P of A times P of B given A. And that's Bayes' theorem for 2 events. 2 possible events. Y'all follow me? This is real important too. And there's a lot, we're going to apply this to a lot of things, and we can extend this. That's Bayesian logic.
Is that like what we had for the quiz part 3? It was like the probability. So if P of A given B, like probability that the switch,
Well, we wanted to do. You're talking about total probability. Here's what we did. I'm going to put it up there the way it appears in the book. So what we wanted for the switch, we wanted, say the switch conducting P of B, and that was equal to P of B given A1 times P of A1 plus P of B given A2 times P of A2 and so forth, where these had to do with the switch being open or closed, and the events A1 and A2 were the probability of switch being open or closed. But that was basically it. This is called Bayes' theorem, and we're going to use this for all sorts of stuff. I'm going to try to not make it confusing, because it'll get real confusing when we get to 4 different events, and we get all like these probabilities. This can go on forever. Like we can get all sorts of different things where you could have P of B given A3 has happened times P of A3, and then you can get all these different permutations of that, but that, I'm not gonna go there now. I want to get that out. Now, okay. I now have to talk about two things that are gonna come to play. And this is one of these things I could bring up now or later, but I'm gonna bring up now, and then I'm gonna show you some examples of how come it's necessary to understand this, even though most of you probably do, before we carry on. Now, let me put up some slides so I can get to the point quicker about a few things. And you have the slides, so it won't be a problem. All right. So first, we're going to talk about the mean of something, or really the average value. So the word mean is really average value. And there's a couple different ways to talk about the average. If you have discrete events, say you just have a bunch of numbers. If I have 1, 5, 7, and 12, call this A right here. Doesn't matter what they represent, their numbers. There's 4 possible numbers there, right? Instinctively, and I think you know this for a fact, if I looked at the average, now anytime we talk about average, it's always a bar like that. In general, the average value is written like this or this. On your calculators, you'll have a U that symbolizes average value. Do you all follow me on this, class? Now, if you look at this, you just add up all these numbers and divide by what? Well, really, the average value is going to be the summation of the values, and I'll call it A of I, from I equals 1 to n, divided by the number of values. This is for discrete operation, or operations that don't have a continuum of values. There's only 4 values here. You with me on this? So you add them up and divide by the number. How many understand that? So I don't have to spend much time. It should be obvious. Now there's something called the standard deviation. Are you familiar with that? All right. And there's a thing called the variance. So the standard deviation the symbol for this is almost always sigma. And that would be the standard deviation. Not always, but almost always. Sometimes they don't use sigma because it means conductivity, or there's another more common association with that symbol. When we talk about the standard deviation, the first thing we have to have is the mean. And usually, I'm going to call it X bar and call it U. That's the mean. So we're assuming we have this. Or the average. To get the standard deviation, what we have to do is start by saying, and these are going to be for discrete events. I'll tell you how to write the formula for this and how it applies to a continuum of values in a bit. But this is going to be equal to, and I'll use X of I minus the mean squared, and you're going to sum that from I equals 1 to n, where you're going to have those. So you get this whole thing summed. And then, in the book, this is in chapter 2, but I don't think I have the page number down. Let me actually see if I can give you a reference so you'll see it. We're going to divide that by n in a second, but send it to you. Then you're gonna divide this by n, the total number. So this is really like the average value of the difference between the single value and the mean squared. And then you have to take the square root of this. Now this is the standard deviation. This is for discrete. I'm going to tell you one other thing. I might as well throw it out now to make this complete, the thought complete. For discrete events, it's straightforward. If you want the mean, add up the things, divide by the number. That's it. There's nothing tricky. The standard deviation, you need the mean to calculate. There's a thing called the mean squared value that we'll get into later. But what that means is you have to have u, the average value, and you subtract, basically you take the value of any item or any value in the ordered pairs, or in the actual set, subtract by mu, square it, sum those up and divide it by n, then take the square root. Now if you think about this, it kind of reminds you of root mean squared with voltage and all that stuff. It's not exact, but it's kind of getting there. By the way, when you hear standard deviation, does it ring any bells about stuff? Have you ever heard, didn't you ever have a professor say the average of the class was this and the standard deviation was this? Now here's the thing. The larger the standard deviation, the greater the spread in values. And if you have a test with an average of say 50 and a spread, a standard deviation of 20 or 30, you're talking about people that are scattered all over the place. What you like as a professor is an average somewhere like 70, 80, somewhere in there, and a standard deviation of like 5, 4, 5. That means most of the people got it. The real widespreads, at least for us, it's an alarm bell. It's like something's really wrong here. Okay. Now I'm going to say this for the continuous type of events too. Tell you what, let me, first I need to show you a PDF of this, or a PowerPoint, but yeah, I better do it this way first. And I think hopefully you'll make sense of what I'm about to say. I have not used this. Y'all mind if I put a slide up for a second? Because it saved me a lot of time drawing. My drawing's not good to begin with. And it's even worse when I'm trying to hurry. I hope this thing works. You've got a guy, you got Ben Smith, right?
Yeah, Ben uses it.
Does he use it?
Mhm.
Okay, good. At least it's been proven at least once. Let's see if I can get this on. And these are the things that always get me. Because they used to have a paper here that says steps to use projector. They don't have it anymore. They just got a lot of stuff laying around.
If you want the thing to come down, the switch on the wall.
Yeah, I'll get that in 1 second. First, I want to make sure this comes on. You have these slides. This will save me time, and hopefully I can understand what you do too. How many have been in here? EMAG 1 or 2?
2.
EMAG 2. Well, you gone through Maxwell's equations, got the general solutions right? I don't know which one. Do you remember which one it is? Oh, it must be this.
I don't know, his laptop's kind of small too. He's got to use like an adapter.
Oh, that's right. I have an adapter. It's using HDMI. All right. Now do me one favor. You pay attention to this. I'll save you some real problems. And I'll tell you why. Because you'll be able to see when I talk about the probability density function where it comes from. Do this first before I mess up. Did you all see that
See what?
message that was on AL.com about Microsoft being compromised in products?
Mm-hmm.
All right. Now, I don't click on a lot of stuff anymore, but I'm trying to make sure that I'm not going to do something. I get any kind of funny business here. All right, now let's see if this works.
Yeah, I think it was like Saturday. I spent most of the morning like changing. I changed all my passwords, but especially anything that was using that password I had for Microsoft stuff.
The two-factor authentication is now something that's been compromised in a lot of places. I don't know if it's here. What's that?
I'll say that's crazy.
You know what's bad about this? The minute they get inside, they can get data that you don't even know is there. Like if you have credit cards on, like I have stuff saved on my computer, the credit card numbers. And that's the last thing I need anybody getting at.
Mm-hmm.
I'm gonna go through this kind of quick. I'm hoping this thing doesn't blitz me. Did you get anything from Auburn University about that or not?
I don't think so.
What that was that Candace thing?
All right, this is straightforward. This is what I just did about, all right, that's total probability, but this is Bayes' rule or Bayes' theorem right here. Can you all see this? Just moving quickly here.
Which section? Down there.
I mean, this is right in chapter 2. If you look at the PDF I put up of the book, it's right in chapter 2, the beginning. But it should be obvious. The application is where it gets tricky. Now what he's trying to do is show you something that's more applicable to the real world and how this stuff actually can be used to calculate information about real world events. Can you all see that, by the way, from wherever you are? So this is a resistor, and if you've got like 1 k ohm plus or minus 5%, what you're really talking about values from 950 to 1050, and that gold, I think you all had this stuff back in the day when you had to read these little carbon resistors. The tolerance gold is 5%. So this is the possible values. And it's when you say something very shortly about what percentage of the resistors are in this range. And I don't remember what it is, but I think it's 3 standard deviations. And so it's almost 100% sure that value, the value of the resistor is within that 5% margin. All right. Now we get into an idea of a random variable. When you talk about a random variable, it's anything where the outcome is not certain. Anything. Rolling a dice, you don't know what's going to happen. Throwing a coin, anything like that. That's all it means. There's nothing tricky about it. You'll notice with that resistor is one thing slightly different. Instead of having discrete values, to all possible values from 950 to 10, or from 950 to 1050 ohms. Do you all follow me on that? So now you've got an infinite number of possibilities. And whenever you talk about the probability of the resistor having a value between, the probability of it having a value of an exact number like 1,000 ohms is actually 0 because, and you'll see this, because the actual area under what's called a probability density curve is going to be 0. I'm getting ahead of myself. Let me just go through this. So this is a continuous random variable, whereas tossing a coin, the outcomes are discrete random variables. That's an obvious fact. Here's something that you're familiar with, grades, exam grades. I don't know if professors put up the exam grades for everybody and try to show information about it, but this is common, I think, in liberal arts and stuff, where they try to show the people, all right, here's all the scores. That doesn't do much for you looking at a whole bunch of numbers, but this is how oftentimes it's shown. And I got to make this point. When you see a histogram like this, what you're seeing is something that's very interesting. You know that this is the frequency of the event, and this is the actual possible value. So you can see almost with your eye, not exactly, but you can see the mean's about there. Can you all follow me on this? And you know the standard deviation, even though not exactly given, is basically going to be something where about 1/5 of the area is under a width of one standard deviation. It's not exactly right, but so you can see the standard deviation is about there, just by looking. But here's where it gets good. We can transform that histogram into something called a probability density function, where instead of a frequency, remember when you take frequency of something divided by total number of something happening, you get the probability of that something. Follow me on this, class? So if we divide these numbers by the total number of events that occurred, we can get something, if we do that, that will be called a probability density function. And if we integrate integrate the probability density function from the lowest possible value to the highest, it has to be 1. I'm throwing this out there fast because I'm about out of time. But you all follow me on this? You'll see how it works. Okay, there's another histogram. Histograms describe how data sets are distributed. It really gives you an idea of what's going on statistically with grades in terms of clustering and all that. And for professors, the thing that alarms a professor is when they get binomial distributions where you get 2 peaks instead of one singular peak where you got people very high and very low. And that's dangerous because that means a lot of people aren't getting it usually. And that's a great concern because we're taught, one of the things, if you're in academia, there are things that are red flags. What you want to do is try to do something to either bring these people to their senses, to work harder or whatever it takes, or alert them that maybe they're not capable of doing what they're being asked to do. And I mean, this is just the reality of engineering and every other field. I'll never be a great artist, trust me. If I ever had to do an art class with the freehand drawings and stuff, it would be one of these things I'd fail as fast as anybody. Okay, now I talked about the histograms. Now we're going to be talking about 2 things. And he tries to do this with resistor values, and I'm going to try to just say this. Remember, the resistor values have values that theoretically could be from 0 to infinity, theoretically. But it has that 5% gold band, and it says most of the value is between 950 and 1050. Now, if you look at something, and this is called a cumulative distribution function, it's saying if I pick a value, and I'm going to on purpose, if I pick a value of 1, well, even though there might be a finite but very small probability, down here, what this is called a cumulative probability, it means the probability of the resistor having a value of 1 or less is about 0. Can you all follow me on this? Now as you come up, you can see about where the 950 is. All of a sudden, the probability that it has a value of 950, it's not measurable on this plot where you can't extrapolate it. But as you look, as it gets further and farther, probability of having 1,000 or less, well, that's about 50%, and he makes it a point to show you that. And the probability has a value of 1,050 or less is about 100%. Now, that's an exaggeration, but it gives you the idea. That's called a cumulative distribution function. Now, listen to the next one. If you took the derivative of this with respect to x, which is the value, you get something called a probability density function. And for this one, because it's shown as a straight line, it would just be square up to here and then back down again. Do you all follow me? We're going to be talking a lot about that, and I want to get this going. Just give me 1 more minute, I'll let you go. All right. There are distribution functions, and there's one basic property that you have. The distribution is the cumulative, it's really the cumulative sum of all the probabilities up to a point. So you pick a point, a value of x, if you have any function at all, and it's going to say the probability, it has a value of x or less is this. It always starts at minus infinity and works upward. But the probability it has an event, the probability of, really of f, the distribution of x, as you get a value of infinity, the largest possible value, it's 1. It has to happen, in other words. Do you all follow me on this? So that's what his point is right here. If you look, it's got a value between 0 and 1, from minus infinity to infinity. The value at minus infinity, the lowest possible value, you could say, is 0. And the value as x goes to infinity is 1. These are just, if you actually look at what they're trying to describe there, it makes perfect sense. It's non-decreasing. You can't have the probability of 1,050 ohms or less being less than the probability of 1,000 ohms or less. It's impossible. So these are self-evident. Now, this is important. The probability of it having a value between x1 and x2 is really the probability of the greater value, x2, minus the probability of the lesser value. I mean, the cumulative probability. And finally, the probability that x is greater than small x is going to be 1 minus the probability it's less than. I am out of time. I will pick it up there. So I'm going to ask you to do some of these homework problems here in chapter 2. For the quiz on Friday, it will be from the homework that I give you in section 10 and 1-10, 1-11, and I'm going to give you a bunch of some additional problems. If you got me on this class, please be serious about this. And I don't think you'll have trouble. Know how to use your calculators. You're allowed to use them. But you have to show me, you know how I got that binomial formula then? You've got to show me what formula you're actually solving. All right. Thank you. Did you understand today? My pain's getting managed a little bit. I can leave this down if it's not there.
Yeah.
Yeah, that's fine.
You know for sure, I'm definitely going to review.
Just probably gonna be like 5.